MIM Virtual Expo 2021.
Hello everyone, and thank you for joining me at the Major Incident Management Expo. I'm very excited to be here talking to you. I wish it could be face-to-face, but these are the days we live in. I work at IBM, and I work in a very interesting position where I am between the clients, helping them get the most out of their operations and incident management tools, and the development teams helping them improve the tools that they are creating. I've been working with IBM for over 10 years now, always in the domain of operations, service management, incident management, of course, and I've been seeing the changes in the industry, the rise of site reliability engineering, the adoption of AI in everything that we do. But what I want to do today is take you back 35 years to the past to one of the largest, most tragic incidents we can imagine, the destruction of Space Shuttle Challenger in January of 1986. I'm very fortunate in that my hobby of the history of space exploration actually has a lot of connection to the work that I do of incident management. And what I want to do today is show you some of the lessons that we can learn from that tragedy in our incident management work today. So we're going to start not 35 years ago, but over 100 years ago. A bit of the context of where space flight actually begins with the history of flight, which started off in 1903, first flight of the Wright brothers, 1927, first flight across the Atlantic, 1947, jet airplanes flying faster than the speed of sound. In 1949, we already start seeing passenger jets that are similar to the ones that we still have today. By 1953, only 50 years after the first man flew, 50 million people had flown in airplanes. Now, a few years after this was the first space flight. Sputnik 1, first satellite in space. 1961, first man in space. 1969, we had already reached the moon and returned safely. So, in just a few years, we had made advances in spaceflight that were very similar to the advances that we had made in flight before then. But not quite. A big difference was that an aeroplane is reused for every flight, whereas a spacecraft, well, the Saturn V rocket that took man to the moon was 110 meters tall, but only 3 meters came back, and that splashed into the ocean somewhere close to an aircraft carrier, which then picked up the astronauts and brought them back safely home. If NASA was to advance spaceflight the same way that airplanes had advanced regular flight, they were nowhere near where they needed to be, because after 10 years, flight was still very much the domain of the few astronauts and cost a lot of money. So they came up with a new generation spacecraft, the Space Shuttle. It would be reusable. It would have a large cargo bay, which could bring a lot of equipment into space with a single launch. They could use it to perform experiments to build space stations. It could return a lot of equipment from space too. So satellites that were damaged or satellites that were nearing the end of their life could be upgraded or repaired, saving money. Also, because it was a large transportation system, we could get people into space who were not only highly trained pilots, scientists, engineers, who would not have to go through years of training in order to fly into space. So the whole point here was to reduce the cost of launching into space, making it more available for others, reducing the danger of each launch, making space travel routine, reducing the uncertainties of space travel. Now, this may sound very similar to what we're trying to do in the modern world with DevOps and cloud-native applications, making deployments easier, making deployments cheaper, reducing the risk of every deployment, minimizing the number of incidents that we have as a result of changes, making things cheaper, simpler, smaller. And the fact of the matter is that, yes, very much the same space shuttle dream is the dream of modern development. How did it work out? Well, at first, things went quite well. 1981, first launch of the Space Shuttle Columbia, and it landed precisely, like an aircraft, at exact position it was supposed to land in the airstrip. No need to mobilize the Navy in order to pick up a spacecraft bobbing in the ocean. And then it flew again. This was the very first time a spacecraft flew twice. By 1982, after a series of test flights, the shuttle was declared operational and could start doing business in space. And the business of the space shuttle was not simply technological or engineering or even scientific, but also cultural. It brought the first American woman into space. It brought the first African American into space. From a business perspective, it started repairing satellites in orbit. The highlights of the space shuttle are probably launching the Hubble Space Telescope and construction of the International Space Station. Now, it's not that all was roses in the shuttle. Shuttle computers, for example, while they flew in the 80s and 90s, were designed in the early 1970s. So let's just compare them to OpenShift. For example, yes, we have multiple redundancy. You had 5 computers in the shuttle, whereas in an OpenShift Kubernetes container platform, again, you have multiple servers to make sure that you have availability. But from a point of view of memory, Space Shuttle computers had less than a megabyte of memory and less than a megahertz of speed for their CPUs. So very, very primitive computers. On the other hand, the deployment of this computer was not in the cloud, but it was high above the clouds. It's only been very recently that computers flying in the International Space Station will actually have enough power to run what we would call modern edge or cloud native applications in space. And I'm very happy that IBM, after having developed the Space Shuttle computers, is continuing to work on edge computing in space. But due to the high costs of the Space Shuttle, due to the slow rate of launch of the Space Shuttle, it still was not making space a normal, a natural thing that anyone could do, just like you get into an aircraft. And so they decided that they would send a regular person into space. A school teacher, Krista McAuliffe, would be the very first civilian, not a NASA astronaut, to fly into space. And her trip on Challenger was scheduled for July of 1985, but it was postponed for technical reasons to November of 1985. It was postponed again to January of 1986. It was postponed again in January, and finally it was scheduled to launch on January 28th, 1986. Tragically, this proved to be the coldest launch day ever, 0 degrees, less than 0 degrees Celsius, less than freezing when the night before the shuttle was launched. The shuttle launched successfully, but 73 seconds after launch, the shuttle disintegrated in mid-flight, and all 7 astronauts were lost. In the investigation of the problem, why did the shuttle fail, they discovered that a small flame started erupting out of the side of the spacecraft, these rocket boosters that you can see. Something was leaking, flame was leaking out, and it struck the large tank of fuel, causing the destruction of the shuttle. Now, in researching why it happened, how did it happen during the various tests that they did, they discovered that within each segment of the rocket booster, and you can see the rocket booster, the size of the rocket booster over here, there were rubber rings which were meant to insulate each layer, each segment from each other. And due to the cold weather, the rubber segments became fragile, brittle, inflexible, and allowed the heat that was coming out of the center of the rocket to leak out and destroy the fuel tank on the side of the shuttle. So the question is, why did they launch when it was so cold? Didn't they realize that the cold would affect the rubber uh, of the O-rings? Well, the engineers did. They did raise red flags saying, look, we're launching the shuttle in unusual circumstances. We think that there's a risk that this is going to cause a problem. And management told them to launch anyway. But was this simply an example of management ignoring the engineering? Was it just someone who was set under pressure to say, well, we've delayed this launch too much, let's launch it now, and I don't care about whatever things the engineers are saying? It's not that simple. Let's look at some of the information that was made available before the decision to launch was made. And I apologize in advance. This is an oversimplification. There was a lot of information available, a lot of information analyzed, but this is a short segment, and I don't want to become too technical. Now, the major objection that the engineers had to the launch was that in previous launches of the shuttle, they had seen that the O-rings, the rubber rings, were damaged. Not enough to cause a failure, but if they had become more damaged, then it would have caused a failure. And they were concerned that lower temperatures were going to make the problem more likely. But when they presented the information to the management was able to say, well, look, you're saying that low temperatures cause damage to the O-rings, but if we look at this graph that you're presenting, we can see that actually when we had a rather high temperature, there was quite a lot of damage. So obviously, Mr. Engineer, there's not necessarily a connection between low temperatures and damage to the O-rings. But if we go a little bit further into the information, we can see that these metrics are only for the flights that had damage to the O-ring. If we take into account all the flights, including the ones where there was no damage whatsoever, we can see that this is an outlier. And as a general rule, as it gets colder, there's more likelihood of damage to the O-rings. Beyond that, if we look at the temperature, the ground temperature, and the day Challenger was launched, we can see that it is far colder than any other previous launch, which means that there's an even higher risk of something going wrong. But what this is called is often normalization of deviance. What this means is that we get used to problems. We've seen damage to O-rings, but this damage didn't cause a problem. The space shuttle, the previous flights, all succeeded despite the problems to the O-rings. So we realize that the damage is not desirable, but also it's not necessarily as dangerous as the engineers are saying. And the shuttle has been proved operational. We've already launched 24 times successfully. We're always late in our deployments. So why shouldn't we just deploy again just like last time? Yes, there was late. Yes, there were problems. Yes, but the shuttle is operational. We've defined it as operational. We think it should launch on time. You haven't proven that this damage is to the O-rings is such a high risk. So let's just continue. So gradually, over the years between the first shuttle launch and the Challenger launch in 1986, NASA had moved from a culture of prove that it's safe to a culture of prove that it's unsafe. Instead of the engineers having to guarantee that the flight would be successful, in order to postpone a flight, they had to prove that the flight would be unsuccessful. And proving a negative is much, much more difficult than proving a positive. And handling technical debt, fixing the problems that we know that exist, but are not necessarily critical problems, becomes much less important than launching the next mission, deploying the next version, releasing the next feature. Now, we can say pretty certainly that NASA learned the lesson in 1986, that normalization of deviance proved that it's unsafe, led to the Challenger failure. But the problem is that in 2003, it led to the Columbia disaster too. 2003, Columbia launched successful mission, but as they were coming back into the atmosphere and the spaceship and the shuttle heated up, it was destroyed during re-entry. And why was it destroyed during re-entry? Well, again, because of something that happened during the launch, and again, because of the normalization of deviance. What happens is that the space shuttle launches, and it's side by side with the fuel tank and the rocket jets. And the side rockets. And what happens is that little pieces of foam, insulation foam, can fall off these components and crash onto the wing of the shuttle. And this had happened before in many other flights, and every time the space shuttle wings were damaged, but not damaged enough to harm the mission, to cause a problem. So what happened? NASA became used to the idea that, yes, there are impacts on the wing, yes, there are problems, but this isn't a severe problem. We can live with this. But on the 1st of February 2003, they could not live with it, and the wing was so severely damaged that the heat of the re-entry tore apart the wing, causing the destruction of the rest of the space shuttle, which broke up over Texas. Again, 7 astronauts lost. So again, the information was brought forward by the engineers to a certain extent. This is a part of a presentation that was done during the flight in order to assess the risk to the astronauts. And all the actionable information is buried in details. It is possible that it could cause significant damage. The flight condition is outside of the test database, meaning that this was beyond the scope of all the tests that they had done, meaning that the engineers could not come to the managers with any guarantee that there was a problem. All they had were their suspicions, and this was not enough for management, again, because management was coming with the position of you have to prove that there's a problem. This was not enough for management to say, yes, we're going to act on this and try to save the shuttle. So modern systems, again, are the same. This is a monitoring graph this is taken out of IBM Observability by Instana, but any monitoring solution is exactly the same. And you'll see that, for example, we have performance issues here that come and go and come and go. And you can easily say, well, I can live with this. I have some periodic issues, periodic peaks, but at the end of the day, it's not actually damaging my system because the system recovers by itself, and I can continue delivering the next feature that I want in my system. But that's not good enough, because one day something else is going to happen. Whatever is causing these symptoms, whatever the underlying root cause is going to be subtly different, or is going to be a slightly different circumstance. In the case of Challenger, it was colder than usual. In the case of Columbia, a slightly heavier piece of foam struck the wing. In your case, it might be a slightly busier day, or a new kind of transaction, or 2 transactions happening at the same time when they never happened before, and suddenly you'll be in a crisis. So we ignore these things because it could have broken, but it didn't. So why should I invest time in these things? But you have to invest time in these things. You have to understand what the underlying reason of a problem is, so that you can avoid the serious problems that might happen in the future. There's a term for that, which is coming out. Safety 1 is avoiding things that are going wrong, and that's all very well. But a much higher quality and a much safer position to be is considered safety 2, ensuring that everything goes right. It's not enough to see, oh, I had a peak and I solved the peak. and I had a peak and I solved the peak. I want to understand why I have these problems and make sure they never happen again. So some of the central lessons that we learned from the shuttle disaster. First of all, from a vision perspective, while I've been concentrating on the failures of the shuttle, we have to take into account that it was a revolutionary spacecraft. And everything that we're talking about today, with all the advances of New Space and SpaceX, Blue Horizons, and so on, they would not have happened without the shuttle. But on the other hand, don't over-engineer beyond your goals. The shuttle was a leap, 2 or 3 leaps too far beyond the spacecraft that came before them. It was much more complicated. It was much more expensive. It was so many unknowns that they had to deal with that in the end they didn't actually achieve their goal of making space travel routine. Okay? Something working in the past, so it's going to continue to be okay in the future, is not a successful strategy. From engineering and management, take into account that a single does-it-all solution, a monolith, if you will, is often more expensive than multiple dedicated solutions. If you have little solutions that do little things, it's much easier to develop, much easier to test them, much easier to make sure that they work properly. Culture leads to errors just as much as technology. The problems at the end of the day, the problems with the shuttle, were not necessarily technological. Challenger would have been fine if they had waited 2 or 3 days for the temperature to rise a little bit. The rubber would have returned to its flexibility, and they would have launched successfully. But the culture of it was okay in the past, so it will be okay in the future, led to the disaster. The fact that management demanded that the engineers prove that there is a problem, not prove that it's safe. Communication, again, from the perspective and now from the engineers, it's very easy to have a gut feeling that something is wrong, but you need to be able to communicate it successfully and justify your point of view, which means perhaps adding more information that is external to the actual technical test. Collaboration, information transfer is key to success. Again, in the case of Columbia, for example, the key information, the actionable information, was hidden deep within PowerPoint slides. If I summarize these central lessons, from a vision perspective, use MVPs. Small steps, quick wins, successful components to define your vision, to fine-tune your vision, to improve your vision. Remember that you're not here to showcase the technology, but you're here to use it. The fact that you're using new features, new technological features, is not important if you're not delivering the business features that you want. From an engineering perspective, avoid normalization of deviance. Don't get comfortable with your technical debt, because it can always come and bite you when you're not ready for it. From a management perspective, don't be satisfied with solving problems. Make sure that problems don't arise. And organizational knowledge, whether it being engineering, business, or management, needs to be shared and stored and kept historically. Otherwise, like NASA, you'll continue repeating the same problems again and again and again. So some further reading if you're interested in this. I've got a blog where I write about these sorts of subjects, the lessons we can learn. Most of my lessons, I'm happy to say, are from happier incidents. For example, lightning striking one of the moon rockets, or the computer restarting just before the first landing on the moon, and still incident management there was successful, and they solved these problems. NASA has a database of a lot of significant incidents and close calls in human spaceflight, a lot of lessons to learn from there. The term normalization of deviance comes from a book written by Diane Vaughan about the Challenger disaster. Fascinating reading, very relevant for any technology, any culture, not just at NASA. And as I said, IBM has our own perspective and point of view on modern service management and operations, and I've included a few links here for you to review. Thank you very much. I hope you've enjoyed this session as much as I enjoyed delivering it to you. And please feel free to reach out to me with any questions. Thank you.
MIM Virtual Expo 2021. MIM